Tiny floating checkerboards are formed when nano-sized blocks spontaneously come together in water. Greetings everyone! Today's video focuses on the fascinating phenomenon of nano-sized silver crystal blocks arranging themselves in water to create a captivating floating checkerboard pattern. This groundbreaking process eliminates the necessity for intricate nanofabrication techniques. Through a collaborative effort between various research groups at UC San Diego, both computational and experimental approaches were employed to design and confirm the structure of these nanocubes. The potential applications of this discovery extend to optical sensing, and future investigations will delve into the optical properties of the checkerboard. Without any further delay, let us dive into our discussion. According to Andrea Tao, a professor at the University of California, San Diego, this method offers a fascinating approach to self-building materials. It eliminates the need for intricate and meticulous processes in a nanofabrication lab. The nanocubes consist of a silver crystal, adorned with a combination of hydrophobic and hydrophilic molecules on its surface. Upon introduction to a water surface, the nanocubes align themselves in a manner where they make contact at their corner edges. This specific arrangement gives rise to a captivating checkerboard pattern with alternating solid cubes and empty spaces. The nanocube's surface chemistry is the driving force behind the self-assembly process. The presence of a large number of hydrophobic molecules on the surface compels the cubes to come together in order to minimize their contact with water. Simultaneously, the extended chains of hydrophilic molecules generate enough repulsion to create empty spaces between the cubes, resulting in the formation of the distinctive checkerboard pattern. In order to construct the framework, scientists utilized droplets of the nanocube mixture and placed them onto a dish filled with water. By submerging a substrate into the water and gradually removing it, the resulting checkerboard pattern can be effortlessly transferred onto the substrate, effectively coating it with the nanostructure. The research presented in this study is the result of a joint endeavor involving various research teams affiliated with the UC San Diego Materials Research Science and Engineering Center, MRSEC. The project showcased a harmonious integration of computational methods and practical experimentation. Tao remarked, "Our approach involved establishing an ongoing feedback loop between our computational analyses and our physical tests. Through computer simulations, we were able to guide the design of nanoscale materials and forecast their behavior. In turn, our experimental findings in the laboratory were used to verify the accuracy of the simulations, refine them, and develop an enhanced model." The selection of silver crystal nanocubes for the material design was based on the expertise of the Tao lab in their synthesis. To determine the most effective surface chemistry, extensive computational experimentation was conducted under the guidance of Gaurav Arya, a professor in the Department of Mechanical Engineering and Materials Science at Duke University and co-senior author of the study. Through simulations, the ideal molecules for attaching to the nanocubes were identified, and the interactions and assembly of the cubes on the water surface were predicted. These simulations were continuously refined, using experimental data provided by Tao's lab. The desired checkerboard structures were confirmed through electron microscopy conducted by the lab of study co-author Alex Frano, a professor in the Department of Physics at UC San Diego. In the realm of optical sensing, Tao envisions a multitude of potential applications for the nanocube checkerboard. She elaborated on the intriguing capabilities of this nanostructure, highlighting its ability to manipulate light in captivating ways. Specifically, the interstitial spaces between the cubes, particularly in the vicinity of the corner edges where they intersect, possess the potential to serve as minuscule hotspots that either concentrate or confine light. This unique property opens up possibilities for the creation of innovative optical components such as nanoscale filters or waveguides. In future studies, the researchers intend to investigate the optical characteristics of the checkerboard. The National Science Foundation and UC San Diego Materials Research Science and Engineering Center, DMR 2011924, provided support for this project. The research was conducted at the San Diego Nanotechnology Infrastructure, SDNI, at UC San Diego, which is a member of the National Nanotechnology Coordinated Infrastructure. The National Science Foundation also supported the SDNI through grant ECCS 2025752. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.